Okay, so I think we're going to get started. Just to let people know, if anybody has any questions, because we have interpreters for both Giordon and for anyone in the audience, you'll need to speak a microphone. So if you have a question, we'll have a microphone up. Let me know, and we'll.
Hi, I'm Jordan. We have 45 minutes to talk, so we're gonna go ahead and just get started really quick. What?
You don't have to use all of it.
Sure. All right, so what we're gonna talk about is the search for supersymmetry and hadronic final states using boosted object reconstruction. Many of you will know what that means, so hopefully we'll be able to cover that today. So there are 5 main central topics that we'll cover. Of these, we're going to talk about the theory, which is the Stirner model, as well as beyond the Stirner model. Then next, we're going to talk about the hardware, which is the Large Hadron Collider and the Atlas detector, which allows us to measure the Stirner model and look for new physics. After that, we'll go ahead and start talking about something more related to a lot of my research, which is about boosted object reconstruction and how to apply that in a search for supersymmetry. And then finally, we'll wrap this all up by looking forward over the next 20 years. So first, the Stirner model and beyond the Stirner model. So we're going to go ahead all the way back in time to about a century ago, where the first particle discovered really was in 1895 with the photon. And this sort of planted the seed for particle physics discovery. And over the next 100 years, it's been a highly collaborative and international effort. And one of the major particle discoveries very recently was the Higgs boson, July 4th, 2012. And we'll talk a little bit more about the Higgs boson very shortly. Now, I should mention this is a very brief table, and there are lots of other particles discovered, but I just decided not to put in this table for the sake of time and interest. So the first thing we're going to do is we have the Stirner model. What is the Stirner model? It's a set of quantum field theory, particularly 2 quantum field theories. One of them is called quantum electrodynamics, which governs the weak and electromagnetic interactions, and 2CD, which is quantum chromodynamics, which governs the strong interaction. Now, of the 4 interactions in nature, strong, weak, electromagnetic, and gravity, the Stirner model does not currently describe gravity right now. We'll talk about that a little bit more in a second, but so on the table at the bottom, you can see the strength of the interaction, where the gravitational interaction is 10 to the negative 41 times smaller than the next smaller interaction, which is the weak. And you can also see the scale difference between all of these forces. So, the Stirner model describes the interactions. It also describes particles. Now, in the Stirner model, there are the 17 particles which you see in the table here. We have the 12 fermions on the left, including the up-down charm strange top-bottom quarks, as well as the 6 lepton, the electron mu1 tau, and the neutrino equivalents. We also have 5 bosons, 4 of which are the force carriers. In particular, for example, the gluon is a force carrier for the strong force. It mediates all the strong interactions. The gluon is also interesting because it actually has a color charge, so it participates in those same interactions. If you look, for example, at the photon over here, which mediates the electromagnetic interaction, the photon has no charge and it does not participate. And then the Higgs boson over here is part of the Higgs mechanism, which we'll talk about very shortly. But the last thing I want to mention is about the masses of all these quarks. You can notice here where each of these spheres, a picture from David, thank you, is where you can see the very big sphere here is the mass of the top quark, where each of the volume is proportional to the masses of the quarks. And you can see that the top quark is significantly greater than pretty much all the other fermions by far, as well as the proton. So there's sort of a scale difference that we've seen in their interactions, but there's also a scale difference in the particles. So how do these quarks get their masses? It's through the Higgs mechanism, which allows for spontaneous symmetry breaking. And what that means is, if we look at a Higgs potential, which has a local maximum here, the Higgs potential will always want to go to a point of lowest energy. When it happens to do that, it turns out this causes spontaneous symmetry breaking. And this is actually where the particles start getting their masses, where you can see where if we started with this interacting term between, say, the B quark and the Higgs field, this actually splits up into a self-interacting term of the B quark. That self-interacting term gives the B quarks their masses, as well as an interacting term with how the B quarks interact with the Higgs through some particular coupling. As said, the next question is, well, we've talked about the quark masses. What about the Higgs masses? So interestingly, the Higgs mass comes out of, when you renormalize a theory, you have to apply some quantum level corrections. It turns out when the LHC announced the discovery of the Higgs boson at 125 GeV, what ended up happening is when you look at the quantum order corrections, those quantum order corrections have a square dependence on the Planck scale, which is the energy scale in which you need to renormalize the theory. So it turns out if this Planck scale is 10 to the 19 GeV squared, then the quantum level correction for the Higgs mass is so large that you have to set the original Higgs mass of the Stirner model to an absurdly large number such that it perfectly cancels out to give you a very small 125 GeV. This is something about naturalness here. It's a very huge fine-tuning, but that's very not natural at all. So there are a couple of questions that I've already raised so far. There's the scale differences between the particles, between the interaction, the fact that there's some sort of fine-tuning on the Higgs mass as well. So there is a lot of theories to try and help sort of rationalize or explain some of these interesting features or perhaps issues. Supersymmetry happens to be one of those frameworks that I'll talk about today. It's a good framework for both theorists and experimentalists to work with because it provides a concrete set of benchmark models that allow experimentalists to answer a lot of these questions, but also get back to the theorists so that they continue more of their work in theory. So let's talk about the supersymmetry. Well, supersymmetry is a quantum field theory. It predicts new boson or fermionic partners for the fermions or bosons of the Stirner model. Pretty much a boson has a fermionic partner and a fermion has a bosonic partner. So you can see the different particles here and how each of the partners relate, where the top line here is for the fermion and the bottom line here is for the bosons. So for example, the gluon, which is in the Stirner model, has a fermionic partner called the gluino. We'll talk about that more towards the search that I'm working on. Oh, how does supersymmetry help with this naturalness, this sort of fine-tuning that I was explaining in the Higgs math? So when you look at the quantum order correction, you want to be able to keep this correction small, and these stop squarks that are predicted by supersymmetry help cancel out those loop corrections on the quantum math, on the Higgs math. And it turns out this actually helps. I keep not pressing the light. And it turns out this helps. So at the end of the day, you're going to have this correction on the Higgs mass and supersymmetry proportional to the masses of the stop squark. So, and actually, if you want to keep this correction small, because otherwise you get into this problem of fine-tuning again, you actually need to have light stops, which is very well motivated. And additionally, because the gluino, through the color interaction, will interact with the light stops, you will want a light gluino instead. Otherwise, it pulls up the mass of the light stop, and the light stops aren't so light anymore. So the last thing we want to talk about is connecting it to the next section about the Large Hadron Collider, which we'll talk about very shortly. So why do we care about searching for, say, gluinos or stops or all of these new particles? How do we pick? So it turns out if we look at the 8 TeV versus 1314 TeV, two different energy levels, you can see that the dashed lines here are for the higher energy level, and then the solid lines for the low energy level. So if we go ahead and look at the red curves and say compare them to the blue curve, you can motivate that gluinos will have a higher cross-section, higher theoretical cross-section, primarily because of the strong color coupling that they have. And so this is actually well motivated to look for at the Large Hadron Collider. So let's go ahead and talk about the Large Hadron Collider because I've started mentioning it a lot. So we need to build a camera. We need to build a camera that takes pictures of proton-proton collisions. So how do we build this camera? There's a couple of ways to do it, but primarily there's two main ways. We have trackers, which use ionization to measure the charged particles. It also uses magnets in those trackers to bend the charged particles and be able to measure the momentum as well. And lastly, we also have calorimeters, which use scintillation and ionization to measure the particle energy. So let's look at the collider. So the collider is located in Switzerland, Geneva, on the left here. And this is a massive 27-kilometer collider that started operations in 2008. There are 4 points along the collider at which the proton-proton beam that circle around the collider interact. And the Atlas detector is one of those detectors located at point 1. So if we go ahead to the next slide, you can see each of these boxes are for each of the interaction points of the Large Hadron Collider. And this explains the geometry a little bit, just so everyone's a little bit more familiar with what we mean by the geometry in Atlas. So Atlas uses pseudo rapidity of eta, where the C direction, which points towards Geneva in the Atlas detector, and then the Y direction, which points straight up from here. Eta will measure the angle between those two, with eta equals 0 pointing straight up, and eta at infinity pointing along the z-axis. Lastly, we also refer to the phi of the particle, which is the angle of the particle in the xy plane. So we also often refer to the energy of these particles in MeV or GeV, which you hear a lot, and those mean giga electron volt or mega electron volt. I will say GeV, MeV, TeV, and so on. Oh, the Large Hadron Collider specifically is a proton collider at 13 TeV center mass energy. Oh, what's really nice, it has an operating peak luminosity, which you can see at the plot at the top left, and it has a proton bunch spacing of 25 nanoseconds, which means that there are 40 million bunch crossings per second. Each of those bunches has a significant number more protons included, which actually means that a bunch crossing will have multiple interactions. Those multiple interactions that we gain in a single bunch crossing are often referred to as pileup, which you can see here in the bottom left, which shows a plot of the mean number of interactions per crossing with the 2015-2016 data run. And you can see that we have upwards of 50 interactions per bunch crossing, which means that there are billions of collisions per second between the protons. That's a lot. And pileup is a big key feature here with the Large Hadron Collider. So, the Large Hadron Collider, as I mentioned, has 4 interaction points. Each of those interaction points has a detector for measuring these particles that come out. So an Atlas detector is one of them and has 4 major subsystems: the inner detector, the muon spectrometer, the calorimeter, and the trigger system. This is a single detector that is 25 meters tall by about 50 meters in length. It's gigantic. It's about the size of the building at Card right over here. And it's composed of 100 million electron channels and over 3,000 kilometers of cables. So let's just briefly take a look inside. So the inner detector is the first stage, first piece, which is the closest to the beam line. And the inner detector is our tracker. It's surrounded by 2 Tesla solenoid magnets containing 4 subsystems here: the insertable B layer, the pixel detector, the semiconductor tracker, and the TRT. The whole point of the inner detector is to identify charged particle tracks as well as reconstruct primary and secondary vertices. Those vertices are important to the identification of particles such as B quarks. This inner detector has a coverage for eta less than 2.5. The other tracker that we have here is the muon spectrometer. It uses 4 Tesla toroid magnets, and it has 4 subsystems as well: the drift tubes, the strip chambers, the resistor plate chambers, and the thin gap chambers. And this has precision measurement of the muon in the detector. And this provides coverage for eta less than 2.7. Now, the next piece we have here is the calorimetry. Because I'm talking a lot about hadronic final state, calorimetry is probably one of the more important pieces of the Atlas detector. So the calorimetry is composed of a lot of different hadronic and electromagnetic calorimeters surrounding this entire thing, where these are sampling calorimeters. What sampling calorimeters mean is that we have layers of dense absorber material, such as lead, copper, tungsten, steel, to reduce the particle energy, and an active material, which is like liquid argon or plastic scintillator, to provide that detectable signal. And you can see that this calorimeter actually provides, when you combine all of these pieces, it provides full eta range up to 4.9 for the detector. And not only does it provide full coverage, but also provides very nice energy resolution as well. The energy resolution is often reported in terms of 3 pieces. The first piece here is a stochastic term proportional to the square root of the energy, and the stochastic term is related to the calorimeter response, sort of how things shower in the calorimeter. We'll talk about showering in a second. The other piece that's proportional to the energy itself about the noise, such as the electronic noise, the readout noise. And then this last piece is a constant term that you just really can't help, such as, that's just slightly imperfect geometry of the detector, the fact that something might be, a picometer off or something. It's just some particular constant term. So we have the calorimeter, we have the inner detector, we have the muon spectrometer. The very last piece to get the Atlas detector working is this trigger system. And so this trigger system has the ultimate job of being able to give us the events we care about. We start all the way up here at 40 megahertz, which is sort of like a fire hose of data. But probabilistically, most of these events are largely uninteresting for the physics program in Atlas. They may be interesting for some other particular physics, but for what we care about, we need to get rid of all of these, but we can't just drop events randomly. We need to have some sort of smart trigger. It needs to be fast and performant to be able to reduce the 40 million events per second down to about 1,000 events per second. And so this trigger is a very important stage because we need to be able to reduce all of this to 1 kilohertz. The main reason for the 1 kilohertz rate is because we're mostly limited by technologies for writing the data to disk. It's really just being able to make sure that we record all that data. We need to keep the rate at about 1 kilohertz. Now, as the Large Hadron Collider starts upgrading the luminosity and you see more data funnel in, you will have the harder time of being able to maintain a trigger without increasing the trigger threshold. You may say, for example, need to increase the threshold on the electron's energy. And as you go to a higher luminosity detector, you're going to have more energy, more higher energy electrons. And if you kept that same threshold, the trigger is going to have a higher trigger rate. So the problem is just increasing the threshold will reduce the rate, which is great, but you may lose efficiency because you were studying some of those lower energy electrons in the first place. So there's a lot of work to be able to keep this trigger fast and performing and keep the rates under control. I'll talk more about my work on this towards the end of the talk today. So let's go ahead and talk about boosted object reconstruction. We've got our theory, we've got the detector, we've got those pictures, but we need to be able to go backwards through those patterns of energy and reconstruct the sort of underlying physics that we're looking at. So here's a diagram of an event in Atlas. A little bit scary, I know. So what it turns out is that there's a hard collision here, and that hard collision is going to radiate showers of partons. Those partons will radiate gluon, which in turn radiate quark anti-quark pairs. And all of that showering happens until a certain point in which the energy of those showered particles will then hadronize because they don't have any more energy left to sort of continue to shower. So then they hadronize to form colorless hadrons. Those colorless hadrons will then get deposited in the detector, which you can see in this sort of cartoon diagram, which I kindly stole from David as well. And so what you see here, you have a proton-proton collision, which forms hadrons. Those hadrons produce patterns of energy, hadronic energy in the event that we would like to reconstruct back into the original showering particles in the first place. So how do we do that? Well, we know that these clusters of energy deposit are going to form predictable patterns. What that means is that a B quark will shower in a very predictable pattern that we can sort of model, and we would like to be able to build a clustering algorithm that reconstructs the B quark from the hadronic pattern that we see in the calorimeter. So all of that energy deposit needs to be clustered back. So those clustering algorithms form objects that we call jets. A very simple name here. Jets are what we call the outputs of clustering algorithms. And so we have clustering algorithms that sort of iteratively goes through all of these energy deposits and tries to form jets out of them. Tries to cluster all of those energy deposits in predictable patterns. So the other thing here is we're going to see jets will sort of look like that. We're going to talk about cone jet algorithms a lot, which is why the jets I showed here look a little bit like cones. So at a low Lorentz boost, at low energy, the jets will sort of shower across some particular area. As we start adding more and more energy into that initial particle that decayed, where we go over to the right here, all of those decay products will sort of start to collimate into a smaller area. But how big is that area? You can actually ask an undergrad or grad student to try and do the physics calculations here using special relativity Minkowski geometry, where you can imagine a pion, sort of a heavy pion compared to the massless photons, will decay. So a pion to two photons here, and you ask, what is the angle between those two photons in the lab frame? And if you do this calculation, which I've done for you kindly in my thesis, you can find that delta R is 2 times the mass of the pion over the transverse momentum of that pion. And what do you conclude from that? The more massive that initial particle is, the more mass it has, the more it decays over a larger area. But if you start boosting that initial pion, giving it more energy, then the smaller the area decays over. Oh, that means if the booster is large enough, are we able to capture the entire decay? The answer is yes. So let's talk about large jets very soon. You can see here we have a hadronic decay of a top quark. A top quark decays hadronically to a B quark and a W boson, which decays to 2 quark. If we ask what is the angle between the B quark and the W boson here, we have this plot that comes from a Monte Carlo generator providing the simulation of physics. And you can see that you have this sort of very nice structure where as you increase the PT of that initial top quark, the energy of that top quark, the delta R between the W boson and the B quark gets smaller as the top quark gets more energy and more boosted. So it's very nice to see this. But we want to be able to capture that entire top quark decay. So we need to use what's called large radius jets. Normally, what Atlas has done in run one, meaning back before from 2008 to 2012 or so, is to take the top of clusters, which were those energy depositions in the calorimeters, put them into the clustering algorithm and form jets. This is it's a little bit slow because there's actually a lot of clusters in that large radius. Another way to do this, however, is to start with smaller radius jets. Smaller radius jets are still built from those same clusters, but over a smaller radius. And then we use the experience of Atlas, or the people in Atlas that have experience in calibrating and correcting these small radius jets for us. We just take those small radius jets, feed them right back in the clustering algorithm, and produce a large radius jet instead. And it turns out this is actually very beneficial, and I've used this in the SUSY search that I'll talk about very shortly. These large reclustered jets help model sort of the patterns of hadron energy that you see in the event and allow us to try and understand whether there are top quarks versus, say, multi-jets. So, putting all of this together into a very nice picture that I made here. This is an example of an event display from the Atlas experiment. You can see the details here, this particular event was in September 8, 2016 at 4:49 in the morning Eastern time. So there was someone on shift taking all of this data. Anyway, so what you see here on the top left, you see these large yellow bars here. Those are the energy clusters that I'm talking about from the calorimeters. Those energy clusters are what are fed into the jet clustering algorithms, the cone jet algorithms, to form the jets that you see here towards the top right. So you can see that jets are formed around a lot of the large energy clusters that are peeking through the cartoon cone there. And you can see different energies where that teal colored jet has 750 GeV, the yellow one here is 600 GeV, and this other guy over here is 400 GeV. And then we also have these light green things, these light green tracks, which you see in the center. And those are the charged particle tracks from the inner detector. This particular event doesn't have any leptons. There are no electrons or muons. And it also has 3 identified B jets, which are large total jet mass, that jet mass coming from the reclustered jets we were talking about. So this sort of event has a lot of hadronic energy in it. The source of energy, the source of final state that we're going to talk about next. So searching for new physics. So we're going to go ahead and search for gluinos. If you remember, gluinos are motivated to be light. They're also copiously produced in the Atlas detector compared to the electroweak production for SUSY. So what are we actually searching for? We have a simplified model here. A very pretty event Feynman diagram, which I believe David actually made this a long time ago. I'm kidding, it was a while ago. So you have here gluinos, which decay through an off-shell stop to 2 tops on each side, so there are 4 tops and 2 neutralinos. Now, the reason I say this is a simplified model is because we don't actually know if Susie is there or not. What we would like to do, though, is maximize the ability of experimentalists to even look for new physics. So what the simplified model does is make a couple of somewhat unrealistic assumptions, such as 100% branching ratio, where you expect 100% of the time for that all-shell stuff to produce a top quark instead of any of the quarks. So it's a little bit unrealistic, but the reason for this is because now we have this 100% branching ratio, it allows us to sort of reinterpret the results of a search on the simplified model to other sort of neighboring searches or neighboring models to see if we see anything anywhere else. This also helps theorists because we can then look for gaps and exploring the phase space of new physics and make sure we leave no stone unturned. The whole point is that it's sort of a collaboration between experimentalists and theorists. So there are two papers here. There's a paper I put out in 2015 as well as in 2016 that you can link. But remember, there are 4 top quarks. Those top quarks are going to produce a lot of hadronic energy in the event. Those neutralinos as well, for example, are a candidate for dark matter. We can't detect them with the detector if they exist. So those are going to look like missing energy in the event. So a typical signature is a large number of B-jets. Each of those top quarks, as you can see in the decay of the top right, will decay mostly into a B quark and a W boson. So each of those tops has a B quark. So there's a lot of B-jets in here. We're going to have a large amount of missing energy from those neutralinos. We're going to have the Lorentz boosted W bosons and top quark in certain regions of perimeter space. So altogether, we have 4 tops in the final state. So we're going to go ahead and look at our pre-selection. The analysis pre-selection just helps us understand the sort of modeling between theory that is based on that the generators produce and compare this to data that we get from the detector. So we have what we call a standard pre-selection for this analysis, which is where we require 4 signal jets. So you can see in this plot, we started 4 jets here for the number of jets, and then we have 2 BTAC jets and missing energy greater than 200 GeV. We have 2 different search regions that we look in. We look in a 0L, a 0 lepton region, as well as a 1L, meaning a 1 lepton region, which, while the name is in the best, means there's at least 1 signal lepton rather than exactly 1. So in this plot that you can see here, for each of the different backgrounds, we have TP-bar in the light blue and all of the other sort of non-dominant backgrounds here. You can see that on the bottom with the ratio plot, the data versus standard model, that this ratio is close to 1, which means at the pre-selection level, things look decently modeled and there's no huge bias from the generators. So now that we've looked at that, we can go ahead and define regions where we can try and be sensitive, incredibly sensitive to Susie. Because at the end of the day, we really want to be able to find Susie. It makes a lot of people happy if we do. So what we're going to do is we're going to define 3 signal regions. If you remember the Feynman diagram, we're going to parameterize all of these regions by the mass of the gluino on the x-axis, the mass of the neutralino on the y-axis. We don't actually know the real masses, so we're going to go ahead and sort of brute force and scan over every possible combination of mass. And we're going to define 3 generic signal regions. We're going to have a boosted region where the gluino and the neutralino have a large split between their masses towards a compressed region where the gluino and the neutralino are closer in mass. So we're going to define 3 signal regions. We're going to define 3 orthogonal control regions. Those control regions are going to be dominated by semi-leptonic TT-bar. Semi-leptonic TT-bar will have 2 tops in the event. That's going to be the dominant background for this analysis, primarily because of the missing energy cut that we apply. So those control regions, because they're dominated by TT-bar, and TT-bar is part of the standard model, we're going to go ahead and fit the Monte Carlo in those regions back to the data. And this derives some sort of normalization. But then we have to ask ourselves, how do we know if the normalization is good? So then we define validation region to somewhat quite literally validate the normalization derived in the control region, which is then applied to the signal region. All right? So what does this region definitions look like? This is a big table. You don't have to memorize this. This isn't a test or anything. But you can see, for example, some of the criterion commoners. You have, for example, 0 leptons in the signal region and then 1 lepton in the control region. That's how you might read this table. And then if you look at each of these different regions between a boosted all the way down to compressed, you can look at some of the different selections we have here. So for example, in the boosted region, we require at least 3 B-jets. And in a more compressed region, we require at least 4 B-jets. So that's another example here. So when we did all this optimization, certain terms such as MJ sum, where MJ sum is the sum of the total jet mass in the event, is the hadronic energy. It turns out that MJ sum was a very nice discriminatory variable that allowed us to be very sensitive to SUSY. So let's go ahead and look at that very quickly. So remember, I showed you all of those selections for each of those region definitions. If you can imagine, we apply all of those selections except for the MJ sum selection, total jet mass, and see what the distribution of that variable is. Now I put a little nice red flag here to let you know what the actual cut is. You can see that the two overlaid lines here are for SUSY, and all of the stacked pretty colors are for the Monte Carlo background, their model background. And you can see that this cut very nicely discriminates between signal and background here. A very strong cut. So this is an example in one particular signal region. Oh, the last thing before we actually go ahead and do all of these fits is that we need to make sure, because we're physicists, we need to understand the uncertainty. We need to make sure we don't just report a number, we report an uncertainty on that number. There are 3 primary systematics that we care about. The systematics on the object. Those are going to be, say, the measurement of a jet momentum. That's where certain things like the jet energy scale calibration comes into play on the bottom left, which has almost a global 1% almost everywhere here. We have a statistical uncertainty, which, could come from the normalization of the TT bar, the semi-leptonic TT bar in the control region. And then we have a theory uncertainty, which you see here on the bottom right, which is about comparing between the alternative generators. The reason theory uncertainties are important to us because SUSY, when we're looking for SUSY, we're looking at these extreme regions of phase space. And those generators are going to be very sensitive to how we model those extremes. So we need to make sure we understand the differences and understand how different each generator models the extreme region of phase space. So you can see here that for an example region, we have 3 primary uncertainties. Like TT bar normalization, theory systematics, and jet energy scale are our main uncertainties. Theory systematics, that makes sense because we're in that extreme region of phase space. And then we have, for example, the jet energy scale. We just have a large hadronic energy, large hadronic final state here. Oh, we've done all of the work. We've checked everything. Let's go ahead and normalize in the control region and check those validation regions. And so the way we check is there's a very pretty plot on the top. But really, we're going to look at the very small piece on the bottom, which shows what we call a pole, which is the difference between, it represents the difference between data and the standard model background here. And you can sort of see the modeling here. We don't see any significant mismodeling here, so we say, great, things are validated. Let's go ahead and unblind and see if we found SUSY in the signal region. So we say, darn, there's no significant difference here too. Okay, so the next step that we do, because we haven't found a significant difference, is we go ahead and define limits. How do we define limits? This is a little bit confusing, so let's talk with a cartoon for a brief second. So remember, we have the mass of the neutralino on the y-axis, the mass of the gluino on the x-axis, and then we draw a yellow curve, which is called our exclusion curve. And below it are where we looked for SUSY, but just didn't find it. That's the region that we've excluded for SUSY. That's a kinematically excluded region, and then this is pretty much what we look at. So let's go ahead and look at the next slide. Now there's 2 limits. On the left here is the limit from 2014. That's not the analysis I was a part of because I'm not that old. However, you can see that this limit has a limit at 1.4 TeV. And then in the 2017 limits here, in the 2015-2016 paper, we were able to increase the sensitivity from 1.4 TeV to just about 2.0 TeV. So we've already increased the limit on the gluino mass from 1.4 TeV to 2 TeV for this particular simplified SUSY model. That's fantastic. So that was the SUSY analysis. Now in the last 10 minutes or so, roughly, we're going to talk about the instrumentation upgrades and maintain the future of Atlas physics program for the next 20 years. This is the other piece of my work with the hadronic energy. So let's talk about motivation. We're going to talk about top quarks again. I love top quarks, third generation, heavy mass, so on and so on. So these high PT Lorentz boosted top quarks here, you can see an example of this event display where the top quark decays to a W boson and a B jet. So this event display has a circle drawn, a black circle of radius 1.0 and 8 of 5 space. And this is a large radius. So the question is, the trigger system that I mentioned before in Atlas, the trigger system has a window size of 0.8. That means if you're looking over a single core here versus this 3-prong, this window is able to capture the full energy of the single prong, but it's not able to capture the full energy of the 3-prong, even though both of them have the same amount of energy. They, for example, came from particle with the same amount of energy, such as the single core came from pion, for example, and the 3-prong came from a top quark decay. So the question is, well, if this window can't see all this energy, it can trigger on this. So we start getting rid of events that may have top quarks. That isn't really good because the SUSY analysis, we were looking for 4 top quarks that boosted. So we start losing efficiency here. So how much efficiency? Oh, the red curve here is the gFEX curve. gFEX stands for Global Feature Extractor, which is the trigger project that I'm working on. The blue curve is the current trigger. Now, ignoring sort of where these thresholds are for the trigger, just look at the energy here at 300 GeV. You can imagine a top quark at 300 GeV will have a radius of about 1.0 from that radius calculation that we just did earlier. You can see that if you look at the blue curve with the blue triangles, you can see that the efficiency is about 70%. So the current trigger system has a 70% efficiency, but these top quarks that I care so much about in this SUSY analysis. The gFEX, however, doesn't really, it just maintains that same efficiency, which means, it recovers the trigger efficiency for just for significant substructure or significant hadronic energy. That's very important for us. So what is gFEX? How does it fit in? So I talked about the detector, and I showed this plot. So what you see here on the left are the calorimeters. You have the tau calorimeter, the liquid argon calorimeter, and the muon spectrometer. Now, the hadronic and electromagnetic calorimeters have fiber optics that feed out into the different feature extractors of the level 1 calorimeter trigger system. We have eFEX, jFEX, and gFEX. gFEX, which is highlighted red for your convenience, is the one that I work on. And so each of these pieces work in parallel towards the upgrade and provide input to the level 1 topological processor, creating a global decision of whether or not to accept the event at that stage of the trigger. What's interesting about gFEX in particular is that it's a single board. We're going to show you a picture of the board in a second. This single board has the entire calorimeter. All of it goes on a single board, and all of the algorithms need to run within the 5 bunch crossing. Those algorithms could be, for example, jet finding algorithm, or estimating the amount of pileup in the event, or trying to estimate the amount of missing energy in the event. All sorts of algorithms that we've thought up and have, will come up again in the next 5 or 6 years that we can then implement on gFEX. Oh, here's a picture of the board. This is not to scale, by the way. The board is only like about, yay big or so, but it's a little bit magnified here. There are 3 blue pieces here, which are our pre-processor FPGA that receive the calorimeter information over 300 fiber optics coming in. And then we have this red piece here, which is the FPGA with a system on chip for slow control and monitoring, and to also do slower and perhaps more advanced physics. Now, what's really nice is that I've been doing a lot of work on this particular FPGA on trying to get the slow control and monitoring working and start looking into all these different algorithms that we can run. Now, one of them is this pileup thing here that we've been talking about, all of those mean interactions. So we have 2 different plots here. That plot on the left is for TT bar, a specific event process. Another one here is for C Higgs. So what you can see on the y-axis for both is the online pileup. Online meaning that we're calculating this in the gFEX. The gFEX is in there, yeah, but we're pretending to calculate it online using the algorithms we would implement. And then the x-axis here is the offline pileup, which is calculated using the offline software in Atlas. a very somewhat complicated procedure. But you can see that we have at least a 90% correlation between online and offline pileup up to a scale difference, which is fine. But that's the whole point. We're able to actually model up pileup really well in real time during the trigger decision path, which is going to be important to enabling all sorts of physics in the future, such as the SUSY searches that we're doing. The last thing is the slow control monitoring here. There's different pictures, which, you know.
On the previous slide,
Yeah.
There's a factor of 2 difference between the two. Why, and why not just normalize it away?
Right. The inputs that we have for the online algorithm are uncalibrated right now, while the offline row is using calibrated. So, you know, the scale difference, I'm not super worried about because you can just multiply by 2 if it's just done. All right, so we have this custom operating system that I've been designing for the board, a very specific procedure, making sure that this is not just for gFEX, but to benefit Atlas as well, of the level 1 calorimeter system. It's very flexible, and right now it can run Python. But if, you know, there's a future new hot technology that wants to be running this will be able to adapt for that because we have to be very forward thinking. This has to last for the next 20 years or so. So there's a lot of different possibilities that you can do for slow control monitoring. These can mean memory mapped access, where you have direct access to the hardware on the board, but we can also do streaming of that data, and we can also do slow control using a web browser if you feel like it, you know, using Chrome or Safari. So there's also use of bleeding edge technology. This particular thing, the FPGA with this embedded processor, also contains a GPU, which is useful because now we can start talking about applications or algorithms that use image-based algorithms, such as clustering for just, or pretty much anything such as pileup calculation, and take advantage of the GPU to do some actual algorithm rather than a modified version to fit in the latency constraints of the system. We still want to make sure that gFEX is useful through the next generation of physicists, which is over the next 20 years of the physics program. And it's hard. You have a single board. That's gonna, hopefully I get to outlive it, but we'll see. So that's the conclusion here. So, you know, we have an instrumentation project that's fully underway to recover the efficiency of hadronic objects with significant hadronic substructure. And I've searched for new physics, didn't find it yet. And we use recluster judge, which allow us to set strong limits on the mass of the gluinos. And then I have pictures of all my different travels that I've met through CERN. There's quite a few, and there's actually 12 different countries in these pictures, if we can identify them. And then I didn't want to leave the committee out, so there are pictures of the committee that I hope are very flattering. Thank you.
Hey, thanks a lot, Giordon. So questions from the committee?
All right, that was really nice. Giordon, so the obvious question is, what's next for you?
What a softball question.
Is that a hard one?
Wow, that was actually easier than I expected. I don't actually have a good answer to the question right now. I'm still applying the job, and you know, we're getting offers. We're gonna deal with it at some point after the defense and the eventual celebration, I hope.
I have a physics question. So you showed this, I think it was the total jet mass sum distribution that had sort of striking power in identifying the signal. Like you don't often see it quite so efficient or something, quite so pure. Is there a simple explanation for why this such a simple seeming variable does so powerful with this selection?
Okay, so in the 2015 analysis, this variable was in there. What we used instead was a simplified top tagging algorithm. I say simplified because what we actually ended up doing is a couple of things. So first, we used recluster checks in the 2015 analysis as well. And those reclusters we try to identify as tops by literally just cutting in the mass of those reclusters. And that showed approximately the same performance as more complicated top tagging by trying to identify B jets and W jets. Those top quarks, when we expect them to decay, we can observe the bare mass. That decay is significantly hadronic energy, and most of that energy is going to show up in the mass, which is effectively just, energy distributed from a distance away from the center of the decay. So what it turns out happened is we then migrated this variable. You can imagine you can ask for, say, 2 tops or 3 tops, and now we're sort of a discrete version of looking at the jet mass of each reclustered jet. But now, using total jet mass, we're a little bit more continuous. We don't have to look at the mass of a single reclustered jet because there could be reconstruction inefficiencies. This variable is very performant because it looks at the total hadronic energy in the event. Because I think I'm going to go backwards. So you can see here, next slide, these 4 tops are producing all of our hadronic energy in the event. And we want to see those 4 tops.
You just don't get that in standard model.
You do. I mean, the TT bars are a dominant background, but to be able to get, something that looks like 4 tops, you just really don't get very close to at the same sort of cross section.
You might add to your response by going back to that plot that you had of M.
Oh, the M one,
and the one that you first.
Oh,
that one, and explaining why there's that big peak in the background. I think that will.
All right, so explain. Wait, what's our question?
Why is there a peak in the background?
Why is there a peak in the background? Let me see for a second. So this particular peak, so I mentioned the major background here is semi-leptonic TT bar. You can imagine, for example, you have a top that you reconstruct. The top mass is around 175 GeV, and so this peak is going to be close enough to it. You might get 2 tops, but since it's primarily semi-leptonic, there's just 1 top that you're looking at.
Plus additional hadronic energy.
Plus addition, yeah.
Or I would say it differently. I would say that that the major background has 2 tops. You miss a little bit of the energy, so it's a little bit below the 350. That's separating it from what he's looking at, which is 4 tops.
I mean, you have to remember, because I've applied all of these other cuts, you have a high missing energy cut. It's really hard to see 2 hadronic tops because we're not that terrible at reconstructing top quarks. So that missing energy is mostly real. It'll come from the neutrino from the decay of the W boson.
Carlos is not here, so I'll ask a question on his behalf. Could you go to your reach limit? The limit figure, the figure that you show the limit. You have an access?
Yes. Good point. I think only the theories were cast out and maybe some particular particle physics tests. So maybe I should talk a little bit more about future plans right now. We are currently doing a next iteration of the analysis, which is including data from the 2017 run. The main thing we're doing right now is we have an excess in one region, a very small 2.1 sigma excess, but we check in again, actually probably next week.
But there should be. Sorry.
Okay, so what Lee and Tao has noticed here is that you can see that this expected limit seems to be a little bit stronger than the observed limit. The main reason that's happening is because if I go back to the previous plot, so what we see here, this is for the cut and count analysis. The cut and count analysis is what I've been talking about. And what this analysis is doing is trying to look for SUSY discovery. We also have a separate parallel analysis, which I'm going to talk about, again, in the interest of time, is to maximize exclusion power. Well, we looked at those regions defined to maximize the exclusion power. Now, these regions, there's a slight excess where there was significant deviation in one of these bins. That significant deviation will correspond to seeing a little bit stronger expected limit than an observed limit in this plot. Does that help answer?
I guess you don't have access in other left-hand channels. Because if you have let's say if you do have access, you should have also access in other left-hand channel, right? Some small access there too.
So you're asking about the different regions, and if we see an excess in one region, whether we see it in different analyses?
The one left-hand analysis.
Yeah, the one left-hand analysis also has an excess, but I don't think we've actually talked about comparing the two to see if they're related yet.
You have a prediction.
For this analysis, we have a prediction of, I think, 2 events in the region that we have an excess.
He's asking, is the excess that you see consistent with an excess that other analyses see?
I don't know that.
Maybe I could also, in terms of future plans, I mean, maybe you can mention that your analysis is basically the first to look at the new data set.
Yeah, so a lot of the work that I've been doing while writing the thesis has been trying to get everybody up to speed on their next iteration of all this work. And we actually on, what is today, Thursday? I think it was yesterday, an Atlas. Yes, where one of the other team members, the contact person for the analysis, actually presented results within Atlas internally to do an unblinding of the 2015-2016 right now to see if the excess is still there and talk about next steps with that. And I think we are pretty far ahead. I mean, we already got the limit plots like a month ago and just been kind of waiting, sort of, which is helping because then I could write my thesis.
Okay, are there other questions from anybody else in the audience? Especially the non-particle physicists.
I mean, there are people on video too if they want to join in.
Yeah, are there people actually connected?
There's like, what, 10, 20 or something.
Oh, okay, yeah, or people on video, which is also why we need to speak into the microphone, I guess. Okay. If not, then let's thank Giordon again. Okay.